Hello class, welcome to the next segment in the vector lecture, and in this next segment we are going to talk about how to convert from the polar convention of vectors to a Cartesian convention of vectors. So in the previous segment we talked about how to convert from Cartesian to polar. Here we're going to cover how to convert from polar to Cartesian, and again this is going to involve more trigonometry, so just something to look forward to as we go through this. So let's actually just go ahead and start off by taking a look at an example vector. So let's consider a velocity vector that is something like follows. Let's say we have a velocity that's 10 meters per second directed at an angle of 35 degrees. And we want to convert this to a Cartesian representation. And the way that you do that is you have to, first you have to, in order to do that, you would have to resolve what the individual x and y components are. And it's easiest to do that if you first take a look at a visual representation of this vector. So if we take a look at a visual representation, so the magnitude of this vector, that is this length of r, that is 10 meters per second, and then the value of this angle theta is in fact 35 degrees. So the reason why I'm keeping this in symbolic form is because this r can represent any magnitude at all of any vector, and this theta can represent any angle of any vector or any direction of any vector. And if you take a look at how this vector is drawn, you can see how it has a part of that vector extends in the x direction and a part of that vector extends in the y direction. And that's going to be our goal. Our goal is going to be to, in order to convert this from polar to Cartesian form, our goal will have to be to resolve what this x component is and resolve what this y component is. So the x is colored in blue and the y is colored in green. And in order to do that, we're going to again have to use some trigonometry here. Now, if we want to resolve the y component, then we have to use the formulation for the sine of an angle. So the sine of an angle theta is equal to the length of the opposite side divided by the length of the hypotenuse. So if we use that definition, then we get that the sine of this angle theta is equal to the y component, which is what we're interested in, divided by the length of the hypotenuse, which in the case of a vector is just the magnitude of the vector, which in this example is 10 meters per second. So now we have to algebraically isolate this y component, and if we do that, we have to multiply both sides by r, and then we can isolate this y component as just being equal to the magnitude of our vector times the sine of the angle that it's directed at. So in this particular example, if we want to calculate the y component, then we just simply take the magnitude, which in this example is 10 meters per second, and multiply the sine of our angle, which is 35 degrees. So to get the y component, we just multiply 10 meters per second times the sine of 35 degrees, and the end result of that is 5.74 meters per second. So that tells us that the y component of our velocity vector is 5.74 meters per second. That means the fraction of this velocity vector that extends in the y direction, the portion of this velocity vector that extends in the y direction is 5.74 meters per second. Now we can do the same thing with the x component, but we can't use sine because sine is the side that's opposite the angle. Instead, what we have to use here is cosine theta. So cosine theta is defined as the length of the adjacent side divided by the length of the hypotenuse. So using that definition, we get that the cosine of this angle theta is equal to the length of the this component, which is the x component, divided by the magnitude of the vector, which in this case is 10 meters per second. So just writing that down algebraically, we get cosine theta is equal to length of the x component divided by the magnitude of the vector in question. And again, we have to algebraically isolate the value of x here. So we get the value of x, or the x component, is equal to the magnitude of the vector times the cosine of the angle that it's directed at, which in this particular case, we would get that the x component is equal to 10 meters per second, which is our magnitude, times the cosine of our angle, which is 35 degrees. So we get that the x component is equal to 10 meters per second times the cosine of 35 degrees, which if we plug that into a calculator, which is in degrees mode and not radians mode, we would get that the x component of our velocity is 8.19 meters per second. And if we want to, so now that we have the individual x and y components, again, the y components up here and the x components down here, now we can write this in terms of our I hat, j hat, and k hat notation, which we looked at in the second segment. And if we do that, we just simply put the x component in front of the I hat unit vector plus sign the y component times the j hat unit vector plus sign, and then any vertical component, which in this case, there's no vertical component. We're only looking in the horizontal direction. And once we've done that, then our work here is done. We've converted this from a polar representation into a Cartesian representation. So that's going to do that for this segment, and in the next segment we will take a look at adding vectors together, adding vector quantities together. So with that, I will see you all in the next segment.